Hello everyone. Welcome to our low temperature thermochronology online lectures. Today, we'll be learning Chapter 4. Chapter 4 is about uranium, thorium, helium thermochronology and analytical techniques. This QR code here will direct you to my university homepage, and you will be able to find more resources about our lectures. This is the outline of this chapter, and first, we'll be starting with crystal selection. The major steps of analytical procedures include, first, separation of ideally intact and inclusion-free mineral crystals. Once rock samples are crushed and target minerals, normally apatites and zircons, are separated using conventional heavy liquid and magnetic techniques before these separates were purified by hand-picking under microscopes. 2. Quantification of size and geometry of each mineral grain in order to estimate alpha ejection correction. 3. Extract and measure helium by heating in a vacuum system. 4. Determine uranium and thorium isotopic composition with spec solutions using SEPMS. And in the end, calculate helium age and correct for alpha ejection. For helium dating, it is recommended running all samples in multi-replicates for a proper data reduction and evaluation. Helium-4 systematics have been determined for a variety of accessory minerals, which preferentially incorporate uranium and thorium, including here apatite, zircon, titanite, monazite, and fluorite, calcite, and hematite. However, uranium, thorium, helium technology is mostly applied using the minerals apatite and zircon. Minerals suitable for uranium, thorium, helium thermochronometry are required to be uranium or thorium-rich accessory minerals such as apatite, zircon, and titanite or monazite, or hydrothermal minerals with non-trivial uranium and or thorium, for example, hematite and fluorite. Metamorphic minerals, for example, garnet and rutile, can also be used for helium dating, and many other materials with measurable helium-4 produced are also suitable for helium dating. This page shows some good examples of uncommonly dated target minerals, such as dating of ore deposit by iron oxides, weathering geochronology by uranium, thorium, helium dating of goethites, and dating of lateritic duracrust from Australia, as well as analysis hydrothermal fluorite, and its result is shown in this isochron diagram. As we have discussed in the last helium theory chapter, wrong ages would be yielded as a consequence of the effect of both uranium or thorium-rich inclusions in low uranium or thorium crystals. For instance, the zircon inclusions in apatite, as well as the effect of uranium or thorium zoning, will be given the wrong ages. To overcome the negative effects on final age data, crystal selection by hand-picking qualified grains is critically needed. Our goal is to select large enough, say prism diameter longer than about 60 microns, intact anhydride crystals. The crystals should also be inclusions, cracks, and fissures free, with no significant zoning and no abraded or coating free. Those fragmentary, subhedral, too small, or dirty appearance grains are impossible ones to measure and should be avoided. Crystal selection is the most important step for good data. As we often say, rubbish in, rubbish out, or RIRO for short. So it is possibly the most time-consuming step of helium dating. Please be picky and be patient. Also remember that not every mineral crystal is usable. For instance, some apatite samples may have excellent fission tracks, but be impossible to date with helium method. Binocular microscope is used as for examinations of morphology and observable impurities. Crystals of preferred geometries are selected round by round until most of the selected minerals are in ehedral and/or regular shape and with relatively clean interior. More dedicated crystal selection imaging mirroring facilities includes high-resolution stereo microscope with a 360-degree rotating polarized stage, polarized analyzer, transmitted and reflected light sources, and bright and dark field capabilities. Crystal mathematics of selected samples are collected using a high-definition camera and interactive measurement software. The fission track mount is actually a very useful proxy for uranium distribution and inclusions. To sum up, the aim of mineral crystal selection process is to produce a pure mineral separates. Screening for mineral or fluid inclusion-rich grains is necessary to use binocular and high-magnification petrographic microscope. Prismatic grains with terminations are preferred to minimize uncertainty in Rayco correction. Minimizing grain diameter variation minimizes the closure temperature variation in slowly cooled samples. There are many approaches used to determine the zonation of apatites, such as fission track or proxy for uranium and thorium by BSE or CL or X-ray spectrometers. These are BSE or in full backscattered electron and CL images of zircons. The bright contrast in BSE and dark contrast in CL are relatively high uranium or thorium zones. In the next section, we'll be discussing crystal characterization in detail. That's all for section 4.1. Thank you for your attention.